Hello and welcome to this video about math. In this video we'll create a computer program that can find all of the antiderivatives of the inverse cosine function up to the nth antiderivative. An antiderivative is the opposite to the derivative, and the first antiderivative is the indefinite integral of a function. So we'll start off with these two definitions. I've defined these coloured letters to stand for these functions so that the screen won't get too cluttered. And this equation is true. It is well known that one is the derivative of the other. And this formula is true. We've derived it in a previous video called the nth derivative of the inverse cosine function. We'll set this red v to be equal to this expression. We'll be using this equation when finding the antiderivatives of c. And this is what v is in terms of u. It is its reciprocal. So now to get the first derivative of v, we'll write this equation using indice notation so as to make it easier to differentiate. We'll expand it out using the chain rule, and so it simplifies to be this. We can substitute u in for this expression to get this equation. And so this is what the first derivative of v is in terms of itself. Now to try to get another expression for v, we'll start with this formula. We can expand it out this way. And so this is what v is in terms of u, when u isn't raised to a power of anything. Now we'll have to use this rule, which is integration by parts, or the product rule for integration. The capital A stands for the first antiderivative of small a. Then we'll substitute these values in for a and b. And this is what the other variables are. We'll get the first antiderivative of c here. We'll then make this substitution into this rule to give us this equation. Then we'll expand the brackets. We can then simplify this equation so that the integral of c times x to the power of n is on one side of the equation. Then we can divide both sides by n plus 1 to give us this equation for this integral. The integrals in these equations are stored in tables, and we can use an expression in a lower part of a table to find the integral for an entry in a higher part of another table. So now to find the equation to find the integral or antiderivative of v times x to the power of n, we'll start with this integration by parts rule and substitute these values in for a and b. And we can derive these values for capital A and B dash. And then we'll substitute these values into the rule. Then we'll expand all the brackets. Then we'll get all of the integrals of v times x to the power of n onto one side of the equation. Then we'll simplify this fraction term. And finally we'll make this integral term into the subject of this equation so as to find this integral for any n. The corresponding value of the integral of c times x to the power of n minus 1 is required, and would be found in its own table, one below the one that we're trying to find. So because these two equations 3 and 4 refer to each other's previous values, we'll have to create a function that can create these tables together. An integral sum can be thought of as a reference to an expression in a table. So this is how an expression is stored in the CXN table. The VXN table is similar, with an array of pointers pointing to the start of each expression in a table array. So this is how an expression is stored in the table array, with each term occupying 3 elements in an array of numbers, and each set of 3 elements coming after each other like this. A term is a collection of numbers and variables multiplied together, and an expression is a collection of terms added together. This is the function that creates both tables for the antiderivatives of CXN and VXN together. We'll set the number of entries found in each table to be 1 to start with. We'll put the first element into the CXN table here, which has 2 terms added together. Then we'll put this into the VXN table as the first entry in the table. So now we'll make a loop to get all of the remaining entries in the tables. We'll set the pointer to the first entry in the construction array, where we'll write the expression for the antiderivative, so that we can do some simplifying of it before writing it into the table. So we'll put the first term in this formula here, circled in red, into the array that's going to be the antiderivative that we're looking for. Then we'll put the second term into this table. Then we'll put this term in that's circled in blue. It's another antiderivative, but because it's the n-1th term of Vx, then we can copy it from the Vxn table. We'll just set up the loop variables here. Start and end are its location in the Vxn table, and m is the multiplier that corresponds to this n divided by n plus 1 term in the formula. So then we'll just copy this entry into the table to the construction array, multiplying the coefficient by m, which means that the term is multiplied by m, and we have to increment the pointer as we copy it to the table. And this variable is the length of the expression in the construction array that we want to simplify, or the number of terms in it. So now we'll simplify this expression in the construction array. We'll then set these variables to point to the start of and size of the ith antiderivative in this table. We'll then copy this entry into the table from the construction array. So now we have the ith entry. We can repeat this step all the way to the nth entry. Then we have to increment the number of entries in this table. So then we'll have to create the Vxn table at the same time. We'll create the ith entry in the Vxn table immediately after we've created the ith entry in the Cxn table. We'll place this term here circled in red into the table. Then we'll place this term circled in green into the table. Then we'll place this term into the table which is the I-1th entry in the Cxn table. So we'll copy this entry from the Cxn table into the Vxn table. We'll copy the number of terms there are in the expression into this variable. We'll simplify this expression. I've discussed these functions in previous videos about similar topics. We'll still have to copy this expression from the construction array where it is now into the table. We'll set these pointers first. Then we'll copy all of the data into the table. Then we'll increment the number of antiderivatives in this table. This is the function that prints out the table in algebraic form. I'll just show it to you without explaining it too much, since I've explained it in another video, and it's easily adapted to any set of variables. And here's the rest of it, since it wouldn't fit on one page. So here's the table of antiderivatives of indefinite integrals of c times x to the power of n. They look fairly simple, like they're not getting huge amounts of terms, except that the coefficients are starting to get complicated. And here's the similar table for the antiderivatives of v times x to the power of n, which is behaving similarly. Now to check that these tables are correct by finding the derivatives of all of these antiderivatives. We're going to check them symbolically, converting the expressions back into expressions, not numbers. So here's an example of how we'll do it. We'll do it for x to the 4th times c. This is what c x to the 4th is from the table. We've stored it in the table as polynomials multiplied by c and v, and no u terms. So now to start to differentiate this expression, we'll start with the first term here circled in red, and we'll expand it out using the product rule. We'll evaluate all of the derivatives in this expression. And then we'll simplify this expression, giving us this expression for the first term. So now to get the derivative of the second term, we'll expand it out using the product rule. And then we'll simplify this expression to get this expression for the derivative of the second term. But there's still more to do. We want to eliminate all of the terms with v and only have terms with c and u. So we'll substitute this equation that we've derived earlier into the derivative that we're calculating. And so after substituting this expression into this equation, we'll get this new equation that we have to simplify. We'll expand all of the brackets, and we'll get this expression after simplifying the expression above it. So now to get the derivative of the third term, we've calculated it to this point where we have to eliminate the term with v. We'll substitute equation 2 into this expression to get this expression, which needs to be simplified. So then we'll expand the brackets. And then after we gather like terms together, we've finished simplifying this expression to give us this as the answer to the derivative of the third term. And now to get the derivative of the last term, which is easily solved with only one term, which gives us this as the derivative of the fourth term, which is extremely simple compared to all the derivatives of all the other terms. So now we can get the derivative of what we found to be the indefinite integral of cx to the power of n. We'll start with what we found in the table. We'll substitute all of the derivatives that we found into this equation and expand all of the brackets. Then we'll gather like terms together, and it looks like a lot of them will cancel. And so they do cancel. So this is the answer. So that what we've found really is the indefinite integral or antiderivative of cx to the power of 4. So now to write up some computer code to find the derivative of c times x to the power of n's antiderivative that we've just found in the table. We'll declare the function with all of its internal variables. We'll get the start and end of this expression in the table using the pointer and size arrays. We'll make up a loop to loop through all of the terms in this expression, and we'll put in the variable k to prevent infinite loops from happening. We'll get each attribute in the array corresponding to each variable of each term. And if the variable is a power of x on its own, then we'll pass on these two terms to the answer. One is just 0 and redundant, but it's easier to pass two terms and eliminate one of them later. And these are the terms for when we find a power of x multiplied by c. And these are the terms when we find a power of x multiplied by u. I tried to not make any of these terms because they are awkward to work with. And this is the second term, which contains a u cubed variable, which can't be properly worked with. But we'll print it out if it ever pops up. I'm trying my best to avoid terms with u in them, and I think I've succeeded. And these are the terms for a term with a v variable. So we'll copy all of these derivatives into the answer array, which is called the construction array. And we'll increment this variable to avoid infinite loops. And the number of terms in the answer is twice the size of what we differentiated, but we still have to simplify it. So this function gets the derivative of every expression in the table and prints them out. It should display the correct version of c times x to the power of n for each of these expressions to be correct. And this is the function to find the derivatives of these antiderivatives of v times x to the power of n. Notice that it contains this new line here, which converts the expression calculated from terms containing u to a term containing v, if this is the form of the expression. So this is the function that converts this expression. We'll declare the function with all of its internal variables. The first condition is that this expression has to have two terms or a length of 2. Then we'll get all of the informational attributes of these two elements, like its coefficient, power of x, and ending functions. The two coefficients must be equal, but we'll allow them to have a very tiny difference, like a billionth, to be equal. So this is where we'll check for equality, being different by no less than a millionth, and the two endings must be equal to u. And one of the powers of x must be equal to 2 plus the other power of x. And if the second power of x is larger than the first, then the coefficients and powers of x need to be swapped. We'll round the coefficient to the nearest millionth here. We'll then set this list to contain this one term or element that contains a v instead this time. And then we'll set the number of elements equal to 1, which is what we'll be expecting if it's correct. So these are the derivatives of all of the antiderivatives in all of these tables of values, being what they were the antiderivatives of in the first place. So then we can use the data in these tables to calculate a table containing the nth antiderivative of the inverse cosine function. So now to look at how we can use the data in these tables to find the nth antiderivative of c. We'll look at an example. We'll get the fifth antiderivative of c from the fourth. So this is what the fourth antiderivative is. We'll get its antiderivative one term at a time and add them all together. So we'll look at the first term in this expression. Then we'll get the first antiderivative of it. We'll evaluate this term in brackets using the table. And then finally we'll expand out the brackets to give us the answer. Then we can look at the second term. We'll get its antiderivative using the table like before. And here's the calculation for the antiderivative of the third term. And here's the calculation for the fourth term. And here it is for the fifth term. So we'll have to add all of these expressions together to give us the final answer. We'll expand all of the brackets. Then we'll simplify the expression, giving us this as the answer. So now to make up a function that can calculate the whole table of expressions up to the nth antiderivative of c, we'll declare the function with all of its internal variables. We'll place the first entry in the table, which is just c on its own. And the location of the first entry is 0 in the table, and its size in the table is 1. And we've only calculated one entry so far. This variable keeps track of how many entries in the table we have. We'll make up a loop to find all of the remaining entries in the table, including the second entry. We'll call this function to get the next entry and place it in the construction array. Then we'll simplify the expression. We'll set these variables so that we can copy this entry into the table from the construction array. Then we'll copy this entry to the table using this function here. So this is the function that calculated the next antiderivative from the previous one. We'll declare this function here. We'll set the location variables of the last expression that we've found so that we can get the next expression from it. We'll set this indexing variable to point to the location in the construction array. That's where we're going to put the next term. We'll loop through every term in the last antiderivative that we've calculated in the table. We'll get information for each term in the entry, like its coefficient, power of x, and trailing function. Then we'll get the antiderivative for this term from the cxn and vxn tables. We'll get its location variables in the table here. This is when its trailing function is c. Then we'll use the cxn table. This is when the trailing variable is u. I just put it in for completeness. It never has to be used, but I'd like to put it in just in case it does get used, as a way of being mathematically tidy. And we'll use the vxn table if its trailing variable is v. So we'll make a loop to get every term in the lookup tables. We'll access the cxn table as the lookup table if its trailing variable is a c. We'll do the same thing if its trailing variable is u, but this code is redundant, and I'm including it for mathematical tidiness like before. And we'll access the vxn table as the lookup table if the trailing variable is a v. This is where we'll multiply the whole expression by a constant outside the brackets. Then we'll write this new term into the construction array, so that all of these expressions are written for each term, one after another, to be added together later. We'll increment the pointer to the construction array here. We'll set this global variable to be equal to the number of terms in the construction array here, after we've written everything to the construction array. And we'll increment the number of entries in the table of antiderivatives of c here, since we're about to copy another expression to it, after we've simplified it. So now to write up the testing function, I'll refer to my earlier videos on how to do this, like the nth derivative of the tangent function. I've used different variables like a, c, v, and u here, but other than that it's the same. So this is the rest of the program, where I calculate the value of the expression and the derivative of the term which is its antiderivative. The changes are circled in red. So this is the rest of the code which remains unchanged. So this is the table of the first 9 antiderivatives of c. The number of terms in each expression is equal to n plus 1, so its order is n. I found this list for 3 functions and the number of terms are the same. The number of terms are always n plus 1. And there are 2 function endings that we can have, and the expression is an even polynomial multiplied by one function and an odd polynomial multiplied by the other. So I hope that you've found this video to be helpful and interesting. Please click like and subscribe if you did. Please leave some helpful and constructive thoughts in the comments. Feel free to share this video, and thanks a lot for watching.